Hello everyone, welcome back to my channel Love Math Tutorial. Today we are going to discuss about real numbers. This is the first chapter of class 10 NCERT syllabus and 8th chapter of Karnataka state syllabus. Now let us start today's class. In the previous session we have learnt about types of numbers and real numbers. In this class we are going to learn about Euclid's algorithm and Euclid's division lemma. Euclid's algorithm is a way to find the greatest common divisor of two positive integers a and b. Euclid's algorithm is a way to find the greatest common divisor of two positive integers a and b. Now, let us learn the definition of Euclid's division lemma. Euclid's division lemma states that for any two positive integers a and b, Euclid's division lemma states that for any two positive integers a and b, there exists a unique integers. Q and R. Here Q is the quotient and R is the remainder, such that A equals BQ plus R, where R is greater than or equal to 0 and less than B. This means that any positive integers can be divided by another positive integer. This means that any positive integer can be divided by another positive integer b with a unique quotient q and remainder r. This means any positive integer can be divided by another positive integer b with a unique quotient q and remainder r, that is a equals BQ plus R. This equation we will be using to solve the problems in this exercise. So, note down the important equation. Now, let us start the exercise 1.1 of NCERT syllabus or exercise 8.1 of Karnataka state syllabus. The first problem in this section is use Euclid's division algorithm to find the HCF of the following numbers. The first problem in this section is 135 and 225. For the given integers 135 and 225, here 225 is greater than 135. Here we are going to apply the Euclid's division lemma. So, by applying Euclid's division lemma, we get A is equal to BQ plus R. Here A is equal to 225 and B is equal to 135. Therefore, 225 is equal to 135 into 1 plus 90. That is, when we divide 225 by 135, we will get the quotient 1 and the remainder is 90. Here the remainder is not 0. So, we have to divide the further. In the next step, we are taking A is equal to 135 and B is equal to 90. That is, 135 is equal to 90 into 1 plus 45. That is, when we divide 135 by 90, we will get the quotient as 1 and remainder as 145. Again the remainder is not 0. So, we have to divide it further. in the next step, A is equal to 90 and B is equal to 45. Here 90 is divisible by 45 and the remainder is 0. Therefore, HCF of 135 and 225 is 45. The second problem is 196 and 38220, that is 38,220. Here 38,220 is greater than 196. Therefore, by applying Euclid's division lemma, A is equal to BQ plus R. Here A is equal to 38,220 and B is equal to 196. Therefore, 38220 divided by 196, the quotient is 195 and the remainder is 0. Therefore, 38220 is equal to 196 into 195 plus 0. Here the remainder is 0. We need not to divide it further. Hence, the HCF of 196 and 38220 is 195. The third problem is 867 and 255. Here 867 is greater than 255. According to Euclid's division lemma, A is equal to BQ plus R. Here A is equal to 867 and B is equal to 255. By dividing 867 by 255, we get 3 as a quotient and 102 as a remainder. So, according to the equation, 867 is equal to 255 into 3 plus 102. Here the remainder is not 0. Hence, we have to repeat the steps once again. Therefore, by Euclid's division lemma, A is equal to BQ plus R. Now, A is equal to 255 and B is equal to 102. By dividing 255 by 102, we get 2 as a quotient and 51 as a remainder. Therefore, 255 is equal to 102 into 2 plus 51. Again the remainder is not 0. Therefore, again we have to repeat the steps. That is, dividing 102 by 51, we get the remainder as 0. Therefore, 102 is equal to 51 into 2 plus 0. Therefore, the HCF of 867 and 255 is 51. Now, let us jump to the next type of questions. The next question is, show that any positive odd integer is of the form 6q plus 1 or 6q plus 2 or 6q plus 5, where q is some integer. Now, let us find the solution. By Euclid's division lemma, we know that A is equal to BQ plus R, where R is greater than or equal to A and less than B. Let a be any positive integer and b is equal to 6. Then a is equal to 6q plus r for some integer q is greater than 0 and r is equal to 0, 1, 2, 3, 4, 5 or r is greater than or equal to 0 or less than 6. Therefore, a is equal to 6q or 6q plus 1 or 6q plus 2 or 6q plus 3 or 6q plus 4 or 6q plus 5. For r is equal to, now let us see what happens to the equation for r is equal to 0. For r is equal to 0, 6q plus 0. 6 is divisible by 2, so it is an even number. For r is equal to 1, the equation becomes 6q plus 1 and 6 is divisible by 2, but 1 is not divisible by 2. So, it is an odd number. Now, let us see for r is equal to 2. For r is equal to 2, the equation becomes 6q plus 2. 6 is divisible by 2 and 2 is also divisible by 2. So, it is an even integer. Now, for r is equal to 3, the equation becomes 6q plus 3. 6 is divisible by 2, but 3 is not divisible by 2. So, it is an odd integer. For r is equal to 4, 6q plus 4. 6 is divisible by 2 and 4 is also divisible by 2. So, it is an even integer. Now, finally, for r is equal to 5, the equation becomes 6q plus 5. 6 is divisible by 2 and 5 is not divisible by 2. So, it is an odd integer. Therefore, any odd integer can be expressed in the form 6q plus 1, 6q plus 3 or 6q plus 5. Now, let us jump to the next problem. An army contingent of 616 members is to march behind an army band of 32 members in a parade. An army contingent of 616 members is to march behind an army band of 32 members in a parade. The two groups are to march in the same number of columns. The two groups are to march in the same number of columns. Then we have to find what is the maximum number of columns in which they can march. What is the maximum number of columns in which they can march? Now, let us find the solution for this problem. Here we have to find the HCF of 616 and 32. So HCF of 616 and 32 is the maximum number of columns in which they can reach. Therefore, by applying Euclid's division lemma, A is equal to BQ plus R. Here 616 is greater than 32. Therefore, A is equal to 616 and B is equal to 32. By dividing 616 by 32, we get the quotient as 19 and the remainder as 8. So the equation becomes 616 is equal to 32 into 19 plus 8. Here the remainder is not 0. So we have to repeat the steps. Now A becomes 32 and B is equal to 8. So the equation becomes 32 is equal to 8 into 4 plus 0. Here the quotient is 4 and the remainder is 0. Since the remainder is 0, we cannot divide it further. Therefore, the HCF is 8. So, according to the question, the maximum number of columns in which they can march is 8. The answer is 8. Now, let us jump to the next problem. Use Euclid's division lemma to show that the square of any positive integer is either of the form 3m or 3m plus 1 for some integer m. Now, let us find the solution. Let x be any positive integer. So, by using Euclid's division lemma, x is equal to 3q plus r, where r is equal to 0, 1, 2. Therefore, x is equal to 3q, 3q plus 1 and 3q plus 2. In case 1, for x is equal to 3q. So, squaring on both sides, we get x square is equal to 3q whole square, which is equal to 9q square. So, x square is equal to 3 into 3 q square. Therefore, x is equal to 3m. In case 2, x is equal to 3q plus 1. By squaring on both sides, we get x square is equal to 3q plus 1 whole square. By using the algebraic identity, a plus b whole square is equal to a square plus b square plus 2ab, we get x square is equal to 3q whole square plus 1 square plus 2 into 3q into 1. X square is equal to 9q square plus 1 plus 6q, which is equal to 3 into 3q square plus 6q plus 1. By taking 3 as common, we get 3 into 3q square plus 2q plus 1. Here m is equal to 3q square plus 2q. Therefore, x is equal to 3m plus 1. Now, let us see case 3. When a is equal to 3q plus 2, squaring on both sides, we get x square is equal to 3q plus 2 whole square. Using the algebraic identity, a plus b whole square is equal to a square plus b square plus 2ab. We get x square is equal to 3q whole square plus 2 square plus 2 into 3q into 2. X square is equal to 9q square plus 4 plus 3 into 4q. X square is equal to 3 into 3q square plus 3 into 4q plus 4. X square is equal to, by taking 3 as common, we get 3q square plus 4q plus 1. I repeat, by taking 3 as common in the above step, we get 3q square plus 4q plus 1, again after bracket plus 1, because we have taken 3 as common. Here m is equal to 3q square plus 4q plus 1. Therefore, x square is equal to 3m plus 1. Hence, square of any positive integer is either of the form 3m or 3m plus 1. Now, let us solve the last problem from this exercise. Use Euclid's division lemma to show that cube of any positive integer. Use Euclid's division lemma to show that cube of any positive integer is of the form 9m, 9m plus 1 or 9m plus 8. Now let us find the solution. Let a be any positive integer. Let a be any positive integer and b is equal to 3. Then the equation becomes a equals 3q plus r, where q is greater than or equal to 0 and r is greater than or equal to 0 or less than 3. Therefore, a equals 3q or 3q plus 1 or 3q plus 2. Therefore, for every number can be represented as these three forms. Let us study the case one by one. By case 1, when a is equal to 3q, cubing on both sides, we get a cube is equal to 3q whole cube. That is, a cube is equal to 27 cube. 27 can be written as 9 into 3. Then a cube is equal to 9m. Here m is equal to 3 cube, where m is an integer such that m is equal to 3 cube. In case 2, when a is equal to 3q plus 1, cubing on both sides, we get a cube is equal to 3q plus 1 whole cube. By using the identity a plus b whole cube is equal to a cube plus 3a square plus b plus 3ab square plus b cube, we get a cube is equal to 3q whole cube plus 3 into 3q whole square into 1 plus 3 into 3q plus 1 square plus 1 cube. A cube is equal to 27q cube plus 3 into 9q square plus 9q plus 1. A cube is equal to 27q cube plus 27q square plus 9q plus 1. A cube is equal to, taking 9 as common, we get a cube is equal to 9 into 3q cube plus 3q square plus q plus 1. Here m is equal to 3q cube plus 3q square plus q. Therefore, a cube is equal to 9m plus 1, where m is any integer such that m is equal to 3q plus 3q square plus q. Now, in case 3, when a is equal to 3q plus 2, cubing on both sides, we get a cube is equal to 3q plus 2 whole cube. Using the identity a plus b whole cube, we get is equal to a cube plus 3a square b plus 3ab square plus b cube. We get a cube is equal to 3q whole cube plus 3 into 3q whole square into 2 plus 3 into 3q into 2 square plus 2 cube. A cube is equal to 27q cube plus 3 into 9q square into 2 plus 9q into 4 plus 8. A cube is equal to 27q cube plus 27 into 2 q square plus 36q plus 8. Taking 9 as common, a cube is equal to 9 into 3q square plus 6q plus 4q. Here we can write 27 as 9 into 3. Therefore, 3 into 2 is 6. Next, a cube is equal to 9m plus 8. Here, m is equal to 3q cube plus 6q square plus 4q, where m is an integer such that m is equal to 3q cube plus 6q square plus 4q. Therefore, the cube of any positive integer is of the form 9m, 9m plus 1 or 9m plus 8. Here ends the first exercise of real numbers. My next video will be uploaded very soon. Thanks for watching. Please like, share, subscribe, follow and don't forget to leave your comments in the comment box. Thank you.